Welcome to my course on becoming an exceptional AI researcher. In this syllabus, I will guide you through the essential skills, knowledge, and tools you'll need to excel in the field. Let's get started. Course: Becoming an exceptional AI researcher. Level Introductory. Instructor: Troy Williams. University Cybersmarts.ai. Course description. This course aims to provide you with a comprehensive understanding of the field of artificial intelligence research. You will learn the fundamental concepts, methodologies, and tools used by leading AI researchers. By the end of this course, you will have the knowledge and skills necessary to pursue advanced research projects in artificial intelligence. Course objectives: understand the fundamental principles and theories of artificial intelligence. Gain proficiency in various AI research methodologies. Develop critical thinking and problem-solving skills in the context of AI research. Learn to use essential tools and software for AI research. Explore cutting-edge research areas and stay updated on the latest advancements in AI. Module 1. Introduction to Artificial Intelligence. Point 1. What is artificial intelligence? Definition of AI. Artificial intelligence is the field of computer science that focuses on creating machines capable of performing tasks that typically require human intelligence, such as visual perception, speech recognition, decision-making, and language translation. Goals and objectives of AI research. The primary goal of AI research is to develop systems that can learn, reason, and act autonomously in complex environments. This involves creating algorithms and models that can process and analyze vast amounts of data, identify patterns, and make decisions based on that information. Real-world examples of AI applications. AI is already being used in various industries, such as healthcare, e.g. medical diagnosis and drug discovery; finance, e.g. fraud detection and algorithmic trading; transportation, e.g. self-driving cars and route optimization; and entertainment, e.g. personalized recommendations and virtual assistants like Siri or Alexa. 1.2 History of artificial intelligence. Early developments: 1950s, 1970s. Turing test. In 1950, Alan Turing proposed a test to determine whether a machine could exhibit intelligent behavior indistinguishable from that of a human. This laid the foundation for evaluating AI systems. Dartmouth Conference. In 1956, a group of scientists, including John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon, held a conference at Dartmouth College to discuss artificial intelligence. This event marked the birth of AI as a formal research field. Early AI programs. Some of the earliest AI programs included the Logic Theorist, 1956, which could prove mathematical theorems, and the General Problem Solver, 1957, which aimed to solve a wide range of problems using heuristics. AI Winters and Resurgence, 1980s, 2000s. Expert systems. In the 1980s, expert systems gained popularity. These AI systems aimed to emulate the decision-making abilities of human experts in specific domains, such as medical diagnosis or equipment repair. Neural networks and machine learning. The late 1980s and 1990s saw a resurgence of interest in neural networks and machine learning. These approaches focused on creating AI systems that could learn from data and improve their performance over time. The role of computing power and big data. The growth of computing power and the availability of large data sets played a crucial role in the advancement of AI during this period. More powerful computers and access to big data enabled researchers to train more sophisticated AI models. Recent advancements, 2010s present. Deep learning. Deep learning, a subfield of machine learning that uses artificial neural networks with multiple layers, has led to significant breakthroughs in areas such as image and speech recognition, natural language processing, and robotics. Reinforcement learning. Reinforcement learning is a type of machine learning where AI agents learn to make decisions by interacting with an environment and receiving rewards or punishments for their actions. This approach has been successfully applied in games like Go and chess, as well as in robotics and autonomous systems. Generative models. Recent years have seen the development of powerful generative models such as GPT-3, Generative Pre-trained Transformer 3, for natural language generation, and DALL-E for image generation. These models can create highly realistic and coherent outputs based on the patterns they learn from vast amounts of data. 3 Types of AI systems. Narrow AI, weak AI. Definition and characteristics. Narrow AI, also known as weak AI, refers to AI systems designed to perform specific tasks or solve particular problems. These systems are focused on a single domain and cannot generalize their knowledge to other areas. Examples. Some examples of narrow AI include image recognition systems that can identify objects in pictures, speech recognition systems that can transcribe spoken words into text, and chatbots that can engage in limited conversations with users. General AI, strong AI, definition and characteristics. General AI, also known as strong AI, refers to AI systems that can perform any intellectual task that a human can. These systems would have human-like cognitive abilities, such as reasoning, learning, and problem-solving, and could apply their knowledge across multiple domains. Challenges and current status of research. Developing general AI is one of the ultimate goals of AI research, but it remains a significant challenge. Current AI systems are still primarily narrow, and creating AI with human-like intelligence requires advances in areas such as common-sense reasoning, transfer learning, and unsupervised learning. Researchers are working on various approaches to achieve general AI, but it is still an ongoing area of research. Superintelligence. Definition and potential implications. Superintelligence refers to an AI system that surpasses human intelligence in virtually all domains. Such a system could have profound implications for humanity, potentially leading to rapid technological advancement or, if not properly aligned with human values, existential risks. Theoretical considerations and long-term goals. The development of superintelligent AI is a long-term goal that raises significant theoretical and ethical questions. Researchers are exploring various paths to superintelligence, such as recursive self-improvement and brain-computer interfaces, while also considering the potential risks and the need for robust safety measures. 1.4 Ethical considerations in AI research. Bias and fairness in AI systems. Sources of bias. AI systems can inherit biases from the data they are trained on, the algorithms they use, or the humans involved in their development. For example, if an AI system is trained on data that reflects historical discrimination, it may learn to perpetuate those biases in its outputs. Consequences of biased AI. Biased AI systems can lead to unfair and discriminatory outcomes, such as perpetuating stereotypes or denying opportunities to certain groups of people. This can have serious consequences in areas like hiring, lending, and criminal justice. Techniques for mitigating bias. Researchers are developing techniques to mitigate bias in AI systems, such as using diverse and representative training data, applying fairness constraints to algorithms, and regularly auditing AI systems for potential biases. Transparency and explainability. The importance of understanding AI decision-making processes. As AI systems become more prevalent in decision-making roles, it is crucial to understand how they arrive at their outputs. Transparency and explainability are essential for building trust in AI systems and ensuring they are used responsibly. Challenges in achieving transparency. Many AI systems, particularly those based on deep learning, are often considered black boxes due to the complexity of their decision-making processes. This can make it difficult to interpret and explain their outputs. Approaches to explainable AI, XAI. Researchers are working on developing explainable AI, XAI techniques, such as feature importance analysis, rule extraction, and counterfactual explanations to make AI systems more transparent and interpretable. Privacy and security. Protecting personal data used in AI training and inference. AI systems often rely on large amounts of personal data for training and operation. Ensuring the privacy and security of this data is crucial to prevent misuse and protect individuals' rights. Securing AI systems against malicious attacks. As AI systems become more integrated into critical infrastructure and decision-making processes, it is essential to secure them against malicious attacks, such as data poisoning, model stealing, or adversarial examples. Balancing privacy and utility in AI applications. There is often a trade-off between preserving privacy and maximizing the utility of AI systems. Researchers and policymakers must work together to find appropriate balances that protect individual rights while enabling the benefits of AI technology. Societal impact and responsibility. Potential effects of AI on employment, education, and social interactions. AI has the potential to disrupt many aspects of society, from the job market to education and social relationships. It is important to consider and address these impacts proactively to ensure a smooth and equitable transition. Ethical guidelines and principles for AI development and deployment. Various organizations such as the IEEE, the European Commission, and the OECD have developed ethical guidelines and principles for the responsible development and deployment of AI systems. These guidelines emphasize values such as transparency, fairness, accountability, and privacy. The role of researchers, policymakers, and society in shaping the future of AI. Shaping the future of AI requires a collaborative effort from researchers, policymakers, and society as a whole. Researchers must prioritize ethical considerations in their work, policymakers must create appropriate regulations and governance structures, and society must engage in informed discussions about the implications and desired outcomes of AI technology. This comprehensive overview of the Introduction to Artificial Intelligence module covers the definition and goals of AI, its historical development, the types of AI systems, and the critical ethical considerations surrounding AI research and deployment. By providing a solid foundation in these topics, this module prepares learners to delve deeper into the technical and philosophical aspects of artificial intelligence in subsequent modules. Module 2, Machine Learning Fundamentals. 201 Supervised Learning. Definition and overview. Supervised learning is a type of machine learning where an algorithm learns to map input data to output labels based on a set of labeled examples. The goal is to learn a function that can predict the correct output for new, unseen inputs. Types of supervised learning tasks. Classification. In classification tasks, the algorithm learns to assign input data to discrete categories or classes. Examples include spam email detection, image classification, and sentiment analysis. Regression. In regression tasks, the algorithm learns to predict continuous numerical values based on input data. Examples include predicting housing prices, stock prices, or weather forecasts. Training process and model evaluation. Training data. Supervised learning algorithms require a labeled data set for training, where each example consists of input features and a corresponding output label. Model training. During training, the algorithm adjusts its internal parameters to minimize the difference between its predicted outputs and the true labels. This process is typically done through optimization techniques like gradient descent. Model evaluation. The trained model is evaluated on a separate test dataset to assess its performance and generalization ability. Common evaluation metrics include accuracy, precision recall, and F1 score for classification tasks, and mean squared error, MSE, or mean absolute error, MA, for regression tasks. Popular supervised learning algorithms. Linear and logistic regression. Decision trees and random forests. Support vector machines, SVM. Naive Bayes. K-nearest neighbors, CAN. 2.2 Unsupervised learning. Definition and overview. Unsupervised learning is a type of machine learning where an algorithm learns to find patterns and structures in input data without the need for explicit output labels. The goal is to discover hidden relationships or groupings within the data. Types of unsupervised learning tasks. Clustering. Clustering algorithms group similar data points together based on their inherent characteristics. Examples include customer segmentation, document clustering, and image compression. Dimensionality reduction. Dimensionality reduction techniques aim to reduce the number of features in high-dimensional data while preserving its essential structure. This can help in data visualization, noise reduction, and computational efficiency. Examples include principal component analysis, PCA, and TSNE. Anomaly detection. Anomaly detection algorithms identify rare or unusual instances that deviate significantly from the norm. This is useful in fraud detection, system health monitoring, and network intrusion detection. Applications and real-world examples. Customer segmentation for targeted marketing campaigns. Topic modeling in text data. Image compression and feature extraction. Anomaly detection in financial transactions or manufacturing processes. Popular unsupervised learning algorithms. K means clustering. Hierarchical clustering. Gaussian mixture models. Principal component analysis, PCA. TSNE, T-distributed stochastic neighbor embedding. 2.3 Reinforcement learning. Definition and overview. Reinforcement learning, RL, is a type of machine learning where an agent learns to make decisions by interacting with an environment. The agent receives rewards or punishments based on its actions and aims to learn a policy that maximizes its cumulative reward over time. Key concepts in reinforcement learning. Agent, the learning entity that makes decisions and interacts with the environment. Environment, the world in which the agent operates and receives feedback. State, the current situation or a condition of the environment. Action, the choice made by the agent at each state. Reward, the feedback signal that the agent receives from the environment based on its actions. Policy, the strategy or decision-making rule that the agent follows to choose actions. Reinforcement learning algorithms. Q-learning, a value-based algorithm that learns the optimal action value function, Q function, to guide the agent's decisions. SARSA, state action reward state action, another value-based algorithm that considers the actual next action taken by the agent during learning. Policy gradient methods, algorithms that directly optimize the agent's policy by estimating the gradient of the expected cumulative reward with respect to the policy parameters. Applications and real-world examples. Game playing, e.g. AlphaGo AlphaStar. Robotics and control systems, autonomous vehicles. Resource management and scheduling. 2.4 neural networks and deep learning. Overview of artificial neural networks. Artificial neural networks, ANNs, are computational models inspired by the structure and function of biological neural networks. They consist of interconnected nodes, neurons, organized in layers, which process and transmit information through weighted connections. Types of neural network architectures. Feed-forward neural networks, the simplest type of neural network where information flows in one direction from input to output layers. Convolutional neural networks, CNNs, specialized neural networks designed for processing grid-like data, such as images or time series. They use convolutional layers to learn local patterns and features. Recurrent neural networks, RNNs, neural networks designed for processing sequential data such as text or speech. They have feedback connections that allow information to persist across time steps. Autoencoders, neural networks used for unsupervised learning tasks such as dimensionality reduction or feature learning. They learn to compress and reconstruct input data through an encoder-decoder architecture. Deep learning and its impact. Definition of deep learning. Deep learning refers to neural networks with many layers, deep architectures, that can learn hierarchical representations of data. Advancements in deep learning, the availability of large datasets, increased computational power, GPUs, and algorithmic improvements have led to significant breakthroughs in deep learning performance across various domains. Applications of deep learning. Deep learning has achieved state-of-the-art results in areas such as image and speech recognition, natural language processing, and game playing. Training deep neural networks. Backpropagation algorithm, the key algorithm for training neural networks, which propagates the error gradient backward through the network to update the weights. Optimization techniques, methods like stochastic gradient descent, SGD, ADAM, and RMSprop are used to efficiently optimize the network's parameters during training. Regularization methods, techniques such as L1-L2 regularization, dropout, and early stopping help prevent overfitting and improve generalization. Challenges and future directions. Interpretability and explainability. Deep neural networks are often considered black boxes, making it difficult to understand their decision-making process. Research on interpretable and explainable AI aims to address this challenge. Unsupervised and semi-supervised learning. Developing methods to learn from unlabeled or partially labeled data is an active area of research as it can reduce the reliance on large labeled datasets. Transfer learning and domain adaptation. Techniques that allow neural networks to transfer knowledge learned from one task or domain to another, improving efficiency and performance. Continual and lifelong learning, enabling neural networks to learn continuously and adapt to new tasks without forgetting previous knowledge, similar to human learning. This module provides a comprehensive overview of the fundamental concepts and techniques in machine learning, covering supervised learning, unsupervised learning, reinforcement learning, and neural networks. By understanding these core concepts, learners will be well equipped to explore more advanced topics and applications in the field of artificial intelligence and machine learning. Module 3, Data Preprocessing and Feature Engineering. 3.1, Data Cleaning and Transformation. Importance of data quality. Data cleaning and transformation are crucial steps in the machine learning pipeline as the quality of input data directly impacts the performance and reliability of the resulting models. Common data quality issues. Missing or incomplete datasets often contain missing values due to data collection issues, system failures, or human error. Noisy or inconsistent data. Data may contain errors, outliers, or inconsistencies that can affect the learning process. Duplicate or redundant data. Datasets may include duplicate or redundant records that need to be identified and handled appropriately. Data cleaning techniques. Handling missing data. Strategies for dealing with missing values include removal, if the missing data is minimal, imputation, filling in missing values based on statistical methods or domain knowledge, or using algorithms that can handle missing data directly. Outlier detection and treatment. Outliers are data points that significantly deviate from the norm. They can be identified using statistical methods, e.g. z-score, interquartile range, or domain expertise. Outliers can be removed, transformed, or treated as separate cases depending on their nature and impact. Inconsistency resolution. Inconsistencies in data, such as varying formats or conflicting information, can be resolved through standardization, data merging, or manual correction. Data transformation techniques. Scaling and normalization. Scaling brings features to a similar range, e.g. between 0 and 1, while normalization adjusts the data to have a mean of 0 and a standard deviation of 1. These techniques help improve the convergence and stability of many machine learning algorithms. Encoding categorical variables. Categorical variables need to be converted into numerical representations for most machine learning algorithms. Techniques include one-hot encoding, label encoding, and target encoding. Handling text data. Text data requires special preprocessing steps, such as tokenization, splitting text into individual words or phrases, stemming or lemmatization, reducing words to their base or dictionary form, and removing stop words, common words like the or and. 3.2 Feature selection and extraction. Importance of feature selection and extraction. Feature selection and extraction help identify the most relevant and informative features for a given machine learning task, improving model performance, reducing overfitting, and enhancing interpretability. Feature selection techniques. Filter methods. These methods assess the relevance of features independently of the learning algorithm. Examples include correlation-based feature selection, chi-squared test, and information gain. Wrapper methods. These methods evaluate subsets of features using the performance of a specific learning algorithm. Examples include recursive feature elimination, RFE, and genetic algorithms. Embedded methods. These methods perform feature selection during the model training process. Examples include L1 regularization, lasso, and decision tree-based feature importance. Feature extraction techniques. Principal component analysis, PCA. PCA is an unsupervised method that linearly transforms the original features into a lower dimensional space while retaining the maximum amount of variance. Linear discriminant analysis, LDA. LDA is a supervised method that finds a linear combination of features that maximizes the separation between classes. Autoencoders. Autoencoders are neural networks that learn a compressed representation of the input data in an unsupervised manner. The learned representation can be used as extracted features. Domain-specific feature engineering. Feature engineering involves creating new features based on domain knowledge or insights from data exploration. Examples include creating interaction terms, aggregating features, or extracting specific patterns from text or images. 3.3 Handling missing data and outliers. Missing data mechanisms. Missing completely at random, MCAR. The probability of a value being missing is independent of both the observed and unobserved data. Missing at random, MAR. The probability of a value being missing depends on the observed data, but not on the unobserved data. Missing not at random, MNAR. The probability of a value being missing depends on the unobserved data, which can lead to biased results if not handled properly. Techniques for handling missing data. Deletion methods, listwise deletion, removing entire records with missing data, and pairwise deletion, using available data for each analysis, are simple approaches but can lead to loss of information and biased results. Imputation methods. These methods fill in missing values based on the available data. Examples include mean, median or mode imputation, regression imputation, and multiple imputation, generating multiple plausible values for missing data. Advanced methods. Machine learning algorithms such as k-nearest neighbors, KNN, or decision trees can be used to predict missing values based on patterns in the available data. Outlier detection and treatment. Univariate methods. These methods identify outliers based on the distribution of a single variable. Examples include using z-scores or the interquartile range, IQR method. Multivariate methods. These methods consider the relationship between multiple variables to identify outliers. Examples include Mahalanobis distance and local outlier factor, LOF. Treatment options. Outliers can be removed if they are confirmed errors or anomalies, transformed, e.g. using logarithmic or Box-Cox transformations, or treated as separate cases for analysis. This module covers essential techniques for data preprocessing and feature engineering, which are critical steps in preparing data for machine learning tasks. By understanding and applying these techniques, practitioners can improve the quality and relevance of their input data, leading to better model performance and more reliable results. The module emphasizes the importance of data cleaning, feature selection and extraction, and handling missing data and outliers, providing learners with a solid foundation in these areas. Module 5, Research Methodologies in AI. 5.1 Experimental Design. Importance of experimental design. A well-designed experiment is crucial for drawing valid conclusions, comparing different AI approaches, and ensuring the reproducibility of results. It involves carefully planning and structuring the research process to minimize bias and confounding factors. Steps in experimental design. Problem formulation. Clearly defining the research question or hypothesis, identifying the variables of interest, and specifying the goals and objectives of the experiment. Data collection and pre-processing. Determining the appropriate data sources, sample size, and data collection methods. Pre-processing the collected data, including cleaning, transformation, and feature engineering, as discussed in Module 3. Model selection and development, choosing suitable AI models or algorithms based on the problem characteristics, data properties, and prior knowledge. Developing and implementing the selected models, considering factors such as model architecture, hyperparameters, and training procedures. Evaluation and validation, selecting appropriate performance metrics and cross-validation techniques as covered in Module 4 to assess the model's effectiveness and generalization ability. Comparing the results of different models and drawing conclusions based on statistical analysis. Controlling for confounding factors. Identifying and controlling potential confounding factors that may influence the experimental results, such as data biases, hidden variables, or environmental factors. Techniques for controlling confounding factors include randomization, stratification, and matching. Reproducibility and documentation, ensuring that the experimental setup, data, code, and results are well documented and reproducible. Providing detailed descriptions of the methods, assumptions, and limitations of the experiment to facilitate replication and validation by other researchers. 552 Hypothesis, Formulation, and Testing. Formulating research hypotheses. A research hypothesis is a testable statement that proposes a relationship between variables or predicts an outcome. In AI research, hypotheses often relate to the performance, behavior, or properties of AI models or algorithms. Types of hypotheses. Null hypothesis, H0. The default or no-effect hypothesis, stating that there is no significant difference or relationship between variables. Alternative hypothesis, H1 or HA. The hypothesis that contradicts the null hypothesis, suggesting the presence of a significant difference or relationship. Hypothesis testing procedure. Specifying the null and alternative hypotheses, clearly stating the hypotheses in terms of the variables and relationships being investigated. Determining the significance level. Setting the threshold, usually denoted as A, for rejecting the null hypothesis, typically 0.05 or 0.01, which represents the probability of a type 1 error, rejecting the null hypothesis when it is actually true. Collecting and analyzing data, gathering relevant data and applying appropriate statistical tests to evaluate the evidence against the null hypothesis. Interpreting the results. Based on the statistical test outcomes, deciding whether to reject or fail to reject the null hypothesis. If the p-value, the probability of observing the data given that the null hypothesis is true, is less than the significance level, the null hypothesis is rejected in favor of the alternative hypothesis. Common statistical tests in AI research. T-tests, used to compare the means of two groups or to test the significance of a regression coefficient. ANOVA, analysis of variance, used to compare the means of three or more groups. Chi-square tests, used to assess the independence or association between categorical variables. Wilcox and rank sum tests, used to compare two groups when the data is not normally distributed. 5.3 Statistical analysis in AI research. Descriptive statistics, summarizing and visualizing the main features of a data set, such as measures of central tendency, mean, median, mode, measures of dispersion, variance, standard deviation, range, and distributions, histograms, box plots. Inferential statistics, drawing conclusions about a population based on a sample of data. This involves estimating parameters, testing hypotheses, and assessing the uncertainty or confidence in the results. Confidence intervals, a range of values that is likely to contain the true population parameter with a specified level of confidence, e.g., 95%. Confidence intervals provide a measure of the precision and uncertainty of the estimated values. Effect sizes, quantifying the magnitude or strength of a relationship or difference between variables. Common effect size measures include Cohen's d for comparing means, correlation coefficients for assessing the relationship between continuous variables, and odds ratios for comparing probabilities. Statistical power and sample size. Statistical power is the probability of correctly rejecting the null hypothesis when it is false. It depends on the sample size, effect size, and significance level. Determining the appropriate sample size is essential to ensure adequate statistical power and detect meaningful effects. Multiple comparisons and corrections. When conducting multiple hypothesis tests simultaneously, the probability of making a type 1 error increases. Multiple comparison corrections, such as the Bonferroni correction or the false discovery rate (FDR) control, adjust the significance level to account for the increased risk of false positives. This module covers the essential research methodologies in AI, focusing on experimental design, hypothesis formulation and testing, and statistical analysis. Understanding and applying these concepts is crucial for conducting rigorous and reliable AI research. By following sound experimental design principles, formulating clear hypotheses, and employing appropriate statistical techniques, researchers can draw valid conclusions, compare different approaches, and contribute to the advancement of AI knowledge. Additionally, emphasizing reproducibility and proper documentation ensures the transparency and reliability of the research findings. Module 6. Tools and Software for AI Research. One Programming Languages for AI. Python. Overview. Python is the most widely used programming language in AI research due to its simplicity, versatility, and extensive ecosystem of libraries and frameworks. Key features: Python offers a clean syntax, strong support for object-oriented programming, and a large standard library. It also has excellent readability and is easy to learn for beginners. Popular AI libraries. Python has a rich set of AI and machine learning libraries such as NumPy, numerical computing, Pandas, data manipulation, and SciPy, scientific computing. R. Overview. R is a programming language and environment specifically designed for statistical computing and graphics. It is widely used in data analysis, statistical modeling, and data visualization. Key features. R provides a wide range of statistical and graphical techniques, including linear and nonlinear modeling, time series analysis, clustering, and more. It also has a large collection of user-contributed packages. AI and machine learning capabilities. R has several libraries for machine learning and AI, such as Caret, classification and regression training, GLEMnet, generalized linear models, and random forest algorithms. Other languages. Java. Java is a general-purpose programming language known for its portability and robustness. It has libraries like Weka and Apache Malib for machine learning and AI development. C++. C++ is a high-performance language often used in resource-intensive AI applications, such as robotics and computer vision. Libraries like OpenCV and lib are popular for AI development in C++. MATLAB. MATLAB is a proprietary programming language and numerical computing environment widely used in academic and research settings. It offers a wide range of toolboxes for AI, signal processing, and data analysis. 6.2 Libraries and frameworks for AI. TensorFlow. Overview. TensorFlow is an open-source library developed by Google for building and deploying machine learning models. It provides a flexible ecosystem for creating and deploying AI applications. Key features. TensorFlow offers a comprehensive set of tools, libraries, and community resources. It supports a wide range of deep learning architectures and provides high-level APIs like Keras for rapid prototyping. Applications. TensorFlow is used in various AI domains, including computer vision, natural language processing, and reinforcement learning. PyTorch. Overview. PyTorch is an open-source machine learning library developed by Facebook. It emphasizes flexibility and allows for dynamic computation graphs, making it popular for research and experimentation. Key features. PyTorch provides a simple and intuitive interface for building and training neural networks. It supports both eager execution and graph-based computation, enabling easy debugging and rapid iteration. Applications. PyTorch is widely used in deep learning research, particularly in areas like computer vision, natural language processing, and generative models. Scikit-learn. Overview. Scikit-learn is a popular Python library for machine learning, built on top of NumPy, SciPy, and Matplotlib. It provides a consistent interface for a wide range of supervised and unsupervised learning algorithms. Key features. Scikit-learn offers a comprehensive set of tools for data pre-processing, feature selection, model evaluation, and model interpretation. It emphasizes simplicity and ease of use. Applications: Scikit-learn is extensively used for tasks such as classification, regression, clustering, dimensionality reduction, and model selection. Other notable libraries and frameworks: Keras, a high-level neural networks API that can run on top of TensorFlow, Theano, or CNTK. Apache Spark, InLib, a distributed machine learning library built on top of Apache Spark, designed for scalability and big data processing. XGBoost, a highly optimized gradient boosting library known for its speed and performance in machine learning competitions. Hugging Face Transformers, a library providing state-of-the-art pre-trained models for natural language processing tasks. 6.3 Data Visualization Tools. Matplotlib. Overview: Matplotlib is a fundamental plotting library in Python, providing a MATLAB-like interface for creating a wide range of static, animated, and interactive visualizations. Key features: Matplotlib allows fine-grained control over every aspect of a figure, including labels, ticks, colors, and styles. It supports various plot types, such as line plots, scatter plots, bar plots, histograms, and heat maps. Integration with AI libraries. Matplotlib is often used in conjunction with AI and machine learning libraries to visualize data, model performance, and results. Seaborn. Overview: Seaborn is a statistical data visualization library built on top of Matplotlib. It provides a high-level interface for creating informative and attractive statistical graphics. Key features: Seaborn offers a variety of plot types tailored for statistical analysis, such as regression plots, categorical plots, and distribution plots. It also provides built-in themes and color palettes for enhancing the aesthetics of the visualizations. Applications: Seaborn is commonly used for exploratory data analysis, visualizing statistical relationships, and presenting the results of machine learning models. Tableau. Overview: Tableau is a powerful and user-friendly data visualization and business intelligence tool. It allows users to create interactive dashboards and visualizations without extensive programming knowledge. Key features: Tableau provides a drag-and-drop interface for creating visualizations, enabling users to quickly explore and analyze data. It supports a wide range of data sources and offers features like real-time data updates and collaborative sharing. Applications: Tableau is widely used in business settings for data exploration, reporting, and creating interactive dashboards for decision-making. Other notable data visualization tools: Plotly, a web-based plotting library that allows creating interactive and publication-quality graphs. D3JAs, a JavaScript library for creating dynamic and interactive data visualizations in web browsers. ggplot2, a powerful plotting system for R based on the grammar of graphics. Bokeh, a Python library for creating interactive visualizations in modern web browsers. This module provides an overview of the essential tools and software commonly used in AI research, covering programming languages, libraries and frameworks, and data visualization tools. Familiarity with these tools is crucial for effective implementation, experimentation, and communication of AI research. Python and R are the most popular programming languages in the AI community, offering a wide range of libraries and frameworks for machine learning and deep learning. TensorFlow, PyTorch, and Scikit-learn are among the most widely used libraries, providing powerful functionalities for building and deploying AI models. Data visualization tools like Matplotlib, Seaborn, and Tableau enable researchers to explore, analyze, and present data and results effectively. By leveraging these tools and software, AI researchers can streamline their workflows, accelerate experimentation, and enhance the impact of their research. Module 7, Advanced Topics in AI Research. 7.1 Natural Language Processing, NLP. Overview: NLP is a subfield of AI that focuses on the interaction between computers and human language. It involves the development of algorithms and models to process, understand, and generate human language in the form of text or speech. Key tasks in NLP: text preprocessing, tokenization, lemmatization, stemming, and removing stop words to prepare text data for further analysis. Language modeling, building probabilistic models to predict the likelihood of a sequence of words or to generate coherent text. Text classification, assigning predefined categories or labels to text documents based on their content. Named entity recognition, NER, identifying and extracting named entities such as person names, organizations, and locations from text. Sentiment analysis, determining the sentiment or emotional tone expressed in a piece of text, such as positive, negative, or neutral. Machine translation, automatically translating text from one language to another while preserving the meaning. Deep learning approaches in NLP. Word embeddings, representing words as dense vectors in a high-dimensional space, capturing semantic relationships between words. Examples include word-to-vec and glove. Recurrent neural networks, RNNs, processing sequential data such as text by maintaining an internal state that captures dependencies over time. Variants like LSTMs and GRUs are commonly used. Transformer models, utilizing self-attention mechanisms to process and generate text, achieving state-of-the-art performance in various NLP tasks. Models like BERT, GPT, and T5 have revolutionized NLP research. Applications of NLP, chatbots, virtual assistants, sentiment analysis in social media, content moderation, and machine translation are some of the prominent applications of NLP techniques. 7.2 Computer Vision. Overview: Computer vision is a field of AI that deals with enabling computers to interpret and understand visual information from the world. It involves the development of algorithms and models to process, analyze, and extract meaningful information from images and videos. Key tasks in computer vision: image classification, assigning predefined categories or labels to images based on their content. Object detection, identifying and localizing specific objects within an image, often by drawing bounding boxes around them. Semantic segmentation, assigning a class label to each pixel in an image, effectively segmenting the image into meaningful regions. Instance segmentation, detecting and delineating individual instances of objects within an image, combining object detection and semantic segmentation. Facial recognition, identifying or verifying the identity of a person based on their facial features. Pose estimation, estimating the pose or orientation of objects or humans in an image or video. Deep learning architectures in computer vision. Convolutional neural networks, CNNs, designed to process grid-like data such as images by learning hierarchical features through convolutional layers. Popular architectures include LeNet, AlexNet, VGGNet, and ResNet. Region-based CNN, RCNN, and its variants, combining CNNs with region proposal methods for object detection. Faster RCNN and Mask RCNN are notable extensions. YOLO, You Only Look Once, and SSD, Single-Shot Multi-Box Detector. Efficient real-time object detection models that predict bounding boxes and class probabilities in a single forward pass. Applications of computer vision. Autonomous vehicles, facial recognition systems, medical image analysis, augmented reality, and robotics are some of the key application areas of computer vision techniques. 7.3. Reinforcement learning algorithms. Overview. Reinforcement learning (RL) is a subfield of machine learning that focuses on training agents to make sequential decisions in an environment to maximize a reward signal. RL algorithms enable agents to learn optimal policies through interaction and feedback. Key concepts in reinforcement learning. Agent, the entity that learns and makes decisions in an environment. Environment, the world in which the agent operates and receives feedback. State, the current situation or condition of the environment. Action, the decision or move made by the agent in a given state. Reward, the feedback signal that the agent receives from the environment based on its actions. Policy, the strategy or decision-making rule that the agent follows to choose actions in each state. Value function, estimates the expected cumulative reward from a given state or state-action pair. Classic reinforcement learning algorithms. Q-learning, a value-based algorithm that learns the optimal action value function, Q function, through iterative updates based on the Bellman equation. SARSA, state action reward state action, similar to Q-learning but considers the actual next action taken by the agent during the update process. Policy gradients, algorithms that directly optimize the policy parameters based on the gradient of the expected cumulative reward, such as reinforce and actor-critic methods. Deep reinforcement learning. Deep Q networks, DQN. Combining Q-learning with deep neural networks to learn the Q function for complex environments with high-dimensional state spaces. Variants and extensions of DQN, double DQN, dueling DQN, and rainbow DQN, which incorporate various improvements and techniques to stabilize and enhance learning. Proximal policy optimization, PPO, a policy gradient method that utilizes a surrogate objective function to ensure stable and efficient policy updates. Actor-critic algorithms combining the benefits of value-based and policy-based methods, using a critic network to estimate the value function and an actor network to optimize the policy. Applications of reinforcement learning, game playing, e.g. AlphaGo and AlphaStar, robotics, autonomous systems, recommendation systems, and resource management are some of the prominent application areas of reinforcement learning algorithms. This module delves into advanced topics in AI research, focusing on natural language processing, computer vision, and reinforcement learning algorithms. These areas represent significant frontiers in AI, with active research and development pushing the boundaries of what is possible. NLP techniques enable computers to understand, process, and generate human language, opening up a wide range of applications from chatbots to sentiment analysis. Deep learning approaches such as word embeddings, recurrent neural networks, and transformer models have revolutionized NLP research and achieved impressive results in various tasks. Computer vision aims to enable computers to interpret and understand visual information, with applications in autonomous vehicles, facial recognition, and medical image analysis. Convolutional neural networks and their variants have been at the forefront of computer vision research, achieving state-of-the-art performance in tasks like image classification, object detection, and semantic segmentation. Reinforcement learning focuses on training agents to make sequential decisions in an environment to maximize a reward signal. Classic algorithms like Q-learning and policy gradients, along with their deep learning extensions, have been successfully applied in domains such as game playing, robotics, and recommendation systems. By exploring these advanced topics, researchers can gain a deeper understanding of the cutting-edge techniques and algorithms driving AI forward. This knowledge empowers them to tackle complex problems, develop innovative solutions, and contribute to the advancement of AI research in these exciting areas. Module 8. Research Paper Writing and Presentation. 8.1 Structure and Components of a Research Paper. Title: a concise and informative title that accurately reflects the content and scope of the research. Abstract: a brief summary, usually 150-300 words, of the research, including the problem statement, methods, main findings, and conclusions. Introduction. Background: provide context and background information to establish the importance and relevance of the research topic. Problem statement: clearly define the research problem or question addressed in the paper. Objectives: state the specific goals and objectives of the research. Related work: review and synthesize relevant literature to demonstrate the current state of knowledge and highlight the gaps or limitations that the research aims to address. Methodology: data collection. Describe the methods used for collecting data, including the data set, pre-processing steps, and any data augmentation techniques employed. Experimental setup. Detail the experimental design, including the models, algorithms, hyperparameters, and evaluation metrics used. Implementation details. Provide information about the software, libraries, and hardware used for implementing the experiments. Results. Experimental results. Present the main findings and outcomes of the experiments, using tables, figures, and charts to visualize the results effectively. Analysis and interpretation. Discuss the significance and implications of the results, comparing them with previous work and highlighting any novel insights or contributions. Discussion. Interpretation of findings. Provide a deeper analysis of the results, discussing their meaning, limitations, and potential applications. Comparison with related work. Compare the findings with those of other studies in the field, emphasizing the novel aspects and contributions of the research. Implications and future directions. Discuss the broader implications of the research and suggest potential avenues for future work. Conclusion. Summarize the main findings, contributions, and significance of the research, reinforcing the key takeaways for the reader. References. List all the sources cited in the paper using a standard citation format, e.g. APA, IEE, or ACM. Appendices, optional. Include additional materials such as detailed derivations, supplementary results, or code snippets that are not essential to the main text but provide useful information for interested readers. Point 2. Effective scientific writing techniques. Clear and concise language. Use simple and direct language, avoiding jargon and unnecessary complexity. Aim for clarity and readability. Logical organization. Structure the paper in a logical and coherent manner, using headings and subheadings to guide the reader through the content. Consistent terminology. Maintain consistency in terminology throughout the paper, defining key terms and acronyms when they are first introduced. Proper grammar and spelling. Ensure that the paper is free of grammatical errors and spelling mistakes. Use spelling and grammar checkers and proofread the paper carefully. Active voice. Write in active voice whenever possible, as it makes the text more engaging and easier to understand. Short paragraphs. Break the text into short, focused paragraphs, each addressing a single main idea. This enhances readability and allows the reader to follow the argument more easily. Effective transitions. Use transitional words and phrases to connect ideas and create a smooth flow between sentences and paragraphs. Proper citation and referencing. Cite all sources accurately and consistently, following the chosen citation style. Use reference management software to facilitate the process. Iterative revision. Revise the paper multiple times, focusing on clarity, coherence, and the overall structure. Seek feedback from colleagues or mentors to improve the quality of the writing. 8.3 Presenting research findings. Oral presentations. Preparing slides. Create clear and visually appealing slides that effectively convey the key points of the research. Use a consistent theme, legible fonts, and appropriate color schemes. Structuring the presentation. Organize the presentation in a logical sequence, typically following the structure of the research paper. Begin with an introduction, provide an overview of the methods and results, and conclude with the main findings and implications. Engaging the audience. Use a clear and confident speaking voice, maintain eye contact with the audience, and use gestures and body language to emphasize key points. Encourage questions and discussion. Timing and pacing. Practice the presentation to ensure that it fits within the allotted time slot. Allocate sufficient time for each section and allow for questions and discussion. Poster presentations. Designing the poster. Create a visually appealing and informative poster that effectively communicates the key aspects of the research. Use a clear and logical layout with a balance of text, figures, and white space. Highlighting key findings. Focus on the most important results and conclusions, using figures and charts to illustrate the main points. Provide brief explanations and context for each element. Interacting with attendees. Be prepared to discuss the research with interested attendees, providing additional details and answering questions. Engage in scientific discourse and welcome feedback and suggestions. Handling questions and feedback. Anticipating questions. Prepare for potential questions by considering the limitations, assumptions, and implications of the research. Have thoughtful responses ready. Responding to critiques. Address critiques and counter-arguments professionally and objectively, acknowledging valid points and providing clarifications or additional evidence when necessary. Incorporating feedback. Use the feedback received during presentations to refine and improve the research, considering alternative perspectives and potential areas for future work. Effective research paper writing and presentation are essential skills for AI researchers to communicate their findings and contribute to the scientific community. By following a structured approach to paper writing, using clear and concise language, and presenting the research findings in an engaging and informative manner, researchers can effectively disseminate their work and foster meaningful discussions and collaborations within the field.